makes it nonstick?
What? You've never heard of polytetrafluoroethylene?
Polytetrafluoroethylene, or PTFE, is a carbon-fluorine polymer that is responsible for the nonstick experience of certain cookware. PTFE has one of the lowest friction coefficients of any solid and has a melting point of over 600 degrees Celsius, making it ideal for high heat applications.
But isn't heating up carbon and fluorine going to make something react?
Nope. The carbon-fluorine bond is strong and non-reactive. It can even be used with corrosive metals and not react.
Let's talk a little bit about the history of PTFE. This takes us back to the 1930s, where Roy Plunkett discovered PTFE in the DuPont-Jackson Laboratory in New Jersey as an accident. He wanted to develop new chlorofluorocarbon refrigerants that were less toxic and was experimenting with TFE gas. On April 6, 1938, he discovered that one of the canisters that should have had airflow out did not, and discovered that there was a whitish powder. What happened was the TFE gas polymerized into a waxy solid we now know as PTFE, with the drum's iron surface acting as a catalyst. It was a happy accident, corrosion resistance and the high heat resistance with low surface friction. Its first application was during the Manhattan Project, to coat the valves and seals in the pipes holding the highly reactive uranium hexafluoride. Then, in 1954, non-stick cooking pans were created by Marc Gregoire at suggestion from his wife, creating the company we now know as Teflon.
So how do you make PTFE? First, you'll need 4 ingredients: fluorspar, hydrofluoric acid, chloroform, and water. Then you put it in a chemical reaction chamber and heat it between 500 and 900 degrees Celsius.
There are 2 main phases in the creation of PTFE. The first phase is pyrolysis, where the creation of the monomer TFE is synthesized out of chloroform, hydrofluoric acid, and fluorspar, as shown here. It's important to note its ideal reaction conditions, which include low pressures at atmospheric pressure and high temperatures, which have shown to favor this reaction. It is also important to note of TFE's flammable characteristic, which means that it's extremely dangerous and its transportation is therefore risky. Therefore, this phase is performed on location of polymerization. Additionally, it is noted that in some procedures, they rapidly cool the product to prevent the reverse reaction from occurring, including the explosive decomposition of TFE. The second phase is radical polymerization, where in water, the use of initiators diacetic acid peroxide or ammonium persulfate is used. To accomplish this, 2 different procedures are technically followed, which include suspension polymerization, where it is milled to produce fine powders for molding, and secondly, dispersion polymerization, where to obtain the colloidal dispersion of PTFE particles can then be crafted into powders as well.
Then, to dive into the chemical reactions behind these TFE, there are 3 main parts. First is the production of chloroform. This uses methane reacted with chlorine gas to produce chloroform. Then, the second step is the production of chloro-difluoromethane. This uses the chloroform from the previous reaction and reacts it with hydrofluoric acid to create the chloro-difluoromethane. And the third step is the polymerization of TFE And although the methods of creating PTFE tend to be trade secrets, there are 2 general methods of creating PTFE. The first includes creating grains of PTFE that can be crafted into pellets to be later molded. The second method produces PTFE in the form of a milk paste and that can later be processed into a fine powder. Now, are there any other uses of PTFE besides the well-known nonstick pan?
While we all love having our food slide right off our pans, there are some other pretty cool uses of PTFE, like Teflon tape, which is used to seal pipes. PTFE is also used for catheters, medical grafts, and as a coating for equipment like forceps and scalpels. PTFE is flexible, non-reactive, and antimicrobial, making it ideal for sensitive medical devices. So,
PTFE does a lot of cool stuff. Why don't we just use it for everything?
That's a great question. Here are some reasons why.
During the production of PTFE, TFE and copper fluoride radicals are released into the atmosphere above 400 degrees Celsius. At 600 degrees Celsius, PTFE releases toxic fumes that can cause physical illness. This is called polymer fume fever. PTFE on nonstick pans are known to be lethal to birds. Leaving the pans on heat over long periods of time releases the fumes and can kill them. Teflon tape on pipes and welding or heat sources near the Teflon tape can cause PTFE emissions and is another point of exposure to humans. PTFE is also a contaminant in tobacco and can cause polymer fume fever to the user.
Wow, I didn't know there was so much behind this pan.